Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's time to start the last day of this IEEE eScience conference, and we're very happy to have an invited talk by Professor Yannis Ioannidis from the National and Kapodistrian University of Athens, which is the main university in Athens, I understand. So Professor Ioannidis got his PhD in computer science at the University of California and is now working in the Department of Informatics. He's been heavily involved in data-centric projects, a lot of EU projects like D4Science, Driver, OpenAir, and so on. And today he will talk about a very interesting topic. The name is Science, D-Science. Please.
Thank you very much. Is this working? Okay. Thank you very much for the introduction, and thank you all very much for being here, on the last keynote of the last day, after the meal we had last night. So you're really brave. So the title of my talk, just to be catchy and get at least you here, is the name is Science, D-Science. And before I start, I just want to many people have mentioned Jim in the previous days, at least day. I was not able to be here Monday or Tuesday, but yesterday many people mentioned him. He was a very good friend who has really changed many of the things that we talk about in this conference, and also in the database field where I come from. And we are approaching the 5-year milestone from when he is missing. So still with his work, Jim is with us. So many people have talked about the science paradigms. I'm not sure if you saw these pictures, which at least I took them from Jim sometime a few years back. The science paradigms that we've experienced are the following. A few thousand years ago, we had the first paradigm where science was mostly empirical, a few models, a few rules, a few theorems, but that was about it. And then the ages went by, and a few hundred years ago, we moved into the theoretical branch where modeling became and generalization became the norm. In both of these eras, we had essentially one scientist in one location working in one discipline. Of course, science was one discipline altogether at that time, studying one phenomenon. And dissemination of the results of his science were done with one pencil and one piece of paper, or in some other times, one carver and one stone. And dissemination of the world was done by the scientist himself or herself in some cases, usually with a street announcement or a letter, and sometimes you could be very enthusiastic and running around naked in the streets talking about the results that you got. The third science paradigm is a few tens of years ago, a couple, I would say, maybe 3, where we got the computational branch, simulating phenomena so that we can get what we want that we cannot get otherwise. And computation and computer science or informatics started becoming very important in that. How did this change the environment? A little bit, but not very much, in the beginning at least. It's still one everywhere. Okay, maybe it's not one scientist, but it's one small group of scientists, still one location, mostly one discipline, one group in some lab. And then, of course, we don't use pencil and paper anymore. We have one file system. And we have one local disk with some custom files that the people did. And then we got into publications, papers, and journals. And now, what we are talking about is the fourth science paradigm, which is data exploration. We solved the computation problem. We can generate lots of data that are running out of our ears. What do we do with that? And that data have a lot of information. And this science paradigm combines all the ones before, because you can get data from observations, you can get data from simulations, you can get data from models. And that's what's being called, e-science. And here, all the ones have disappeared, and now everything is many or large. Many scientists, many locations, many disciplines, many phenomena, many pieces of software, many different ways to store the data or represent the data and so on. And then, how do you publish this stuff? The traditional stuff is still around, but many, many other ways exist. So the world is a lot more diverse, a lot more uncertain when we are into this four-science paradigm. So this is called e-science. And looking back at the definition, at least the one I found, says that e-science is computationally intensive science that is carried out in highly distributed network environments, which was kind of the third paradigm, or science that uses immense data sets that require computing. Well, the first one is solved. What we are faced now, the way we predominantly do science now, is the second line. And it talks about data, okay? So it shouldn't be e-science, it should be D-science. And often we forget about that. Often we don't realize that we need to have specialized techniques on data management in order to be able to do the science that we want. So if we want to remember it, I suggest I would change the name of the conference from e-science to D-science. So let's see. We see tremendous dependence on any kind of science, not just natural sciences, but the humanities, social sciences, and so on the analysis of data in order to be able to have the scientific discovery that we are after. And a year or so ago, even Nature came back and said, hey guys, data management should be woven into every course in science. So everyone should learn a few things about data management. Hopefully not to take my job away, okay? But in order to have an understanding of the data so that certain things are not set up right. I claim that yes, this should be done, but this is not enough. And unless data specialists, whether it's in the management of data or in the analysis of data, get involved hand in hand, okay, sleeping together with the domain scientists who know and we need to do the science themselves, we'll end up with failures. So let's see what is the research life cycle. And you are, I don't know, 40 people in the room. You could draw 41 such cycles. This is my cycle. It's my talk, it's my cycle. Hopefully it correlates with yours. So we have some piece of scientific knowledge. Nothing, is born out of nothing. And then step one, you conceive and you study what exists and you conceive a new theory or a new hypothesis and you design an experiment. And then in step two, you collect your data. In step three, the experiment data, you need to organize it so that you can make this data manageable, store it, curate it, and so on and so forth. Then you analyze it in step four to get data patterns, what data hides in it. Then the scientist, number five, interprets it to come up with a scientific discovery, and then it disseminates the results in step number six. More or less okay? Well, what is the scientist's role in this? In the early times, this scientist was doing all 6 steps from beginning to end, okay? There was no issue of scale in data, so there was no trouble doing that. In the current times, certain things have been given to others. Publication, dissemination has been given to professionals. Data collection, you have instruments and so on and so forth. The scientist typically doesn't construct, or specialist constructors, engineers that construct the colliders or the telescopes are employed for that. Not the astronomer is not building telescopes. The scientists, out of these 6 steps, step number 1 and step number 5 is definitely the astronomer or the physicist that should be doing that. But currently, still in the data organization and data analysis, these have not been given away. The scientists themselves are doing it. It's not our helping to do it. It's not guiding and instructing what they need out of the data. They are doing it itself. And I think this is wrong. it cannot go as far as we can go in a different way. So if we look at the scientists' roles with respect to informatics and what we need from them, this is one of Jim's slides. The scientists need to tell us what kind of data they need and what kind of questions they need to be asking of the data. And the rest should be done by others. We should have the miners, the analysts, who know the intrinsic algorithmic details on how to get statistical stuff out of it. The plumbers, being the data management database people. My picture should be there. And then, okay, some software engineers to create tools and various other applications. But the domain scientists should be removed of the burden to handle the data themselves. They should outsource this, of course, in interaction. So, if this is the research life cycle, I won't talk about this because I don't know nothing about astronomy or physics or anything, and I won't talk about that. And I will use this as my way of capturing the agenda. I'll talk about these things. A little bit of each one to show you some things that data management hides and we need to pay attention to, or some developments. Also, if this is some research work's life cycle, and we think of it as one piece of work, one scientific endeavor, and we have another one, often these two need to interact. And then the issue of interoperability comes in at a whole bunch of levels. And I'll say a few things about that. And then, if we consider that, okay, we have this, and the scientist that thinks around it, uses it to do their science, and yes, we have another one, and we have a whole bunch of others, the question is, should we move all of these systems and build one data infrastructure that gives you the entire life cycle, and therefore serve everyone with this? And I'll say a few things about that as well. So, data management. I'll talk about data organization first. Data collection, I don't have much to say. Just to say, with respect to data management, with my team, it's a large team with some colleagues of mine and a whole bunch of students and other colleagues. We are about 50 people. We're working on a whole bunch of things in database and information systems, but often, most of our work is related to particular applications, and physical sciences, lots of them, I'll give you examples. Cultural heritage, e-health are an important part of what we do. So whatever I'll say in the rest of my talk, whether explicitly or implicitly, comes from my experience and our experience in dealing with problems like this. And also the other one I want to mention is electronic infrastructures, digital libraries, digital repositories, things that try to do the last thing I mentioned, serve many people and not building a system at a time. So, some reds that are the important things from that. Okay, I should have removed this innovation. And the particular projects that we are running right now are varied enough, not in their data management challenges so much, but in their applications. So, ESPAS is about near-Earth space, and I'll have a couple of slides on that. D4Science was about environmental monitoring. iMarine is about fisheries and marine life. Earth Server is about earth sciences and earth observations. Interactive is about Arctic environment. Greece is an Arctic state, so it participates next to Siberia and Greenland and so on. But when you do data management, you can do it anywhere, so that's a privilege. Going on the other side, humanities and culture, EFG is about European films and how to handle them. Chess is about museum storytelling. Biomagnetic resonance is BMRB, and OpenAir is publication monitoring. So you see, data management is the center of almost 10 very different activities coming from very different sciences. This is very important. It means that certain things can be abstracted away, And data management here means data management there. But that's limited. Beyond this, it's a scientist who knows what they want, and it's a scientist who should guide the entire process. So, ESPACE is about near space. It tries to bring together many different scientific communities that deal with near Earth: space weather, space climate, ionosphere, magnetosphere, thermosphere, many spheres I didn't know that existed. I learned because of ESPACE. And there are many industrial users besides the scientific communities that are interested in what is going on in near Earth. Okay, and you can see the Earth and what near means. It's a few thousand kilometers out. Okay, the space domain, you have one of the worst situations because you have multidisciplinary case studying the same area for different purposes, and even the scientists don't know how to interact among themselves in scientific terms. They don't have the same language. And they don't have the same policies about using the data. They don't need them in the same way to use them. They don't have the same structures that they have in mind. They want to ask the same things. So the kind of data and the kinds of ways that you have to present the same data is very diverse. Having all the data in files, which is the predominant way of dealing with scientific data nowadays, doesn't cut it. Because then everybody will be getting that same file and processing it on their own. But we don't want the scientists to spend time in computer science. We want the scientists to spend time in their science. Data modeling, so it's very important. If people say, well, data modeling, this is 30 years ago, it's solved. Well, no, ladies and gentlemen, it's not solved. When we want to do this science for real, we have to go back to the roots with a clean slate and white piece of paper, and certain things, you use the experience of the past, but certain things, you do them. For policies, I won't even say, it's a nightmare. What is the infrastructure that could be used in there? And the key thing, data in data management are typically used for queries. What is the average salary among my employees? Here, this is not enough. You want to process the data in much more complicated ways. You want to take them through models, compare them, change them, transform them, approximate them. And you end up with what may be called scientific workflows. Not the business workflows of how you get an insurance, but scientific workflows. How does a data management system serve scientific workflows on top? And I'll say a few things about that. D4Science was about environmental monitoring and fisheries. Again, the European Space Agency and the Food and Agriculture Organization were involved, two very different organizations, very different fights internally, and then, of course, externally. Here we have sensor data. Very different beast. Certain principles the same, but you need to, SQL, our Nobel keynote yesterday said, many astronomers know SQL. I was grinding my teeth. Poor them. Poor astronomers that had to learn SQL. Okay, and now SQL doesn't cut it. Okay, they learned SQL. It doesn't take them where they need to go. iMarine, fisheries and marine life, cultivated fish and natural fish, what's happening in the oceans, very important. Their economics go in the picture, and biodiversity. Every species is so different from the other, so that the representation, their data representation internally, in order to be able to ask smart queries, differs. Work needs to be done on that. Earth server. We leave the Earth and we go and look at it from above. The atmospheric, oceanography, geology, and general Earth observation communities. Again, multidisciplinarity. Predominantly, if you remember in my slide about the fourth paradigm, many phenomena are studied together in today's D-science, or science, for that matter, to get there. And people have already started dealing and coming up with data management systems that store the data, not just the metadata, whatever metadata means, and the data being in files. Store the metadata in appropriate ways. And again, this kind of science doesn't work. The data structures that work for this kind of data, for this kind of science, doesn't work for another. So specialized knowledge and research needs to be done on that. In general, currently, every case, well, until very recently, I should say, in every new scientific problem, people start and build software from scratch. Okay, let's build something that will serve the needs of this. Let's build software that will serve the needs of that. And this is a lot of time and money and effort wasted. And not only that, because often it's not done with the right expertise, a lot of things are done with not the in-depth knowledge that would be required to get the optimum solution. A consistent informatics perspective in what is being done is missing, and that's a problem. So what are common challenges? Okay, this is the obvious one: managing and processing exponentially growing volumes of non-collocated data. The data will never be in the same place because it's not generated in the same place. And transferring data, yes, we have grid FTP and we can transfer a petabyte in so many days, but then the next month we will need it somewhere else. We cannot be doing this. We need to deal with data where it is and send processing there. Very interesting challenges in scheduling. Data is time sensitive, is geo-located, and it comes from sensors that may fail. It's uncertain. Data that data management people haven't been dealing with until now. But they need to pair up and work on them. Data cleaning, because of that uncertainty, is very challenging. Specialist storage and data structures I mentioned. Efficient querying and distribution. The current data technology that exists doesn't cut it for complex scientific workflows to optimize them and run them as efficiently and as accurately as possible. On the other hand, there is technology that can be specialized, that the data management field can bring into the picture and handle the data in order for these science to work appropriately. Parallelism should be there, cloud, grid, whatever your favorite buzzword is, or the buzzword of the day. One of the things that saves business data management is that more or less all of us do the same thing. We go to the ATM and we ask for $100 from the machine. So everyone runs this query. It has been optimized to death. A scientist every day asks a different question, a different query. So there are no predefined patterns. So the system should be optimizing more or less on the fly. Extreme challenge. Or trying to identify weird patterns that particular scientists use or need, and then be prepared for that. Another big challenge. So work needs to be done there. If you do all this on top of a data management system, so please bring me the data, forget what you're telling me, get me the data and I'll do what is necessary, well, you're not getting the best mileage out of your data. Because doing it, whatever you need to do close to the data, inside the data management system, I don't mean Oracle and SQL Server, and I'm sorry for the Microsoft and Oracle people in the room, okay? I don't mean the current relational or relational-like systems. I mean new, specialized data management systems or data management components that serve this kind of data. Do whatever you need to do in there, close to the data. You have to gain a lot. Parallelism, structures, optimization, and so on. And currently, this is not the case. We are not doing it in that way. And that's why we need to work on this science. Let's focus. Data is is king or queen, okay, and we need to play with its rules. There are some efforts recently. By the way, the fact that scientists and data management people don't dance every day and every night is the fault of both. Both our community and the scientists' communities are at fault. At fault is in quotes, okay? There are recently, I mean, there have been attempts for at least 20 years to dance a tighter dance. Sometimes it's worked, sometimes it's failed. Recently, there seem to be some initiatives from data management, from the data management community, that is really pushing in this direction. And we have CyDB in the US with Mike Stonebreaker from MIT and Wisconsin and Washington and Michigan and Oregon. Very good piece of software trying to address earth sciences. It seems that earth sciences are the easiest. Bio is the worst, and I'll explain why. Earth sciences, when you can put everything you know in a Manhattan geometry, so to speak, okay, it seems that this is easier. So everyone is working on that. So the US side is working on that, and Razdaman with Peter Baumann and MonetDB with Martin Kirsten are doing work, and they are collaborating. And they have scientists around them. So there is hope. But we need to be doing this from dawn to dusk. Space is evolving extremely fast, hyper-exponentially. The details are not important. The shape and the projection is that, but not for all sciences. If you look at bio numbers, these graphs are a couple of years old, but bio numbers, yes, they grow, but they don't grow as fast. Whereas we are talking about terabytes and petabytes in the earth sciences and natural sciences in general, when you go to bio, you talk about megabytes, okay, maybe gigabytes. You can get to terabytes if you stretch things, but not yet. So bio is easy. No, because bio, yes, it's smaller, but it's much more complex. This is a tiny database schema, relational, mind you. Okay, so you astronomers, you know SQL, so whoever is astronomer can write queries on this because you had to learn SQL. This is about 350 tables just to capture NMR data that comes out of NMR. NMR people who helped develop this, often they're not sure what means what, and they keep changing it. Oh, I didn't capture it in the appropriate way. Okay, you have a few megabytes, okay, hundreds of megabytes. So it all fit in memory. It's not a computational issue, okay? Complexity is immense there. So when we talk about this science, it depends on the science on whether the issue is scale or complexity, meaning conceptual scale. And part of, especially bio, other sciences as well, is that there are so many data banks, the bio people call them banks, okay, that they are interrelated, and data is copied from one to the other, and then you end up with inconsistencies. How do you deal with inconsistencies? And a whole bunch of that. That's another picture that just to scare you. So if we look overall picture of a data system that will try to solve something at some level generically, and beyond that in a special way, in principle, you need to take into account lots of kinds of data, streams, static data, domain expertise, ontologies that exist, and so on. Build your basic data management skills, data management services, and these data management services often are different from the traditional ones. The topics are the same, but the way you need to solve them are different. And that's where data management research comes in order to serve these science. Data management technology is not there for everything that you need to do in these science. On top of it comes step number 4, analyzing the data, okay? Coming up with models for the data or the users of the data. And then through some language, have externally various tools, visualization, workflows, and stuff like that. And they should be dynamic. As data changes, the tools should be changing, and so on and so forth. And this is a great data management challenge. In the next 10 years, a bunch of people will be working on something like this. And the efforts that I mentioned earlier are moving in this direction. Data management people cannot do it on their own. Scientists cannot do it on their own for different reasons each side. But this is where we're going. And it's not that we'll build one of these and we'll be done. Okay? Many of these will be around. So let me give you a couple of examples, and I'll be skipping some things. Let's talk about query optimization. Query optimization says you ask a question, you just say what you want, not how the system will get it. And the system, because it knows what you're asking in SQL, what are the operators that are hidden behind your question, and knows your data, some statistics about your data, can figure out what's the fastest way to do it. But now in scientific databases, you want to process not a query, but a scientific workflow. And the workflow has operators in it that you don't know what they are. They are arbitrary. They are this model. They are FFT. They are this transformation that your graduate student wrote and then further process it. How do you optimize it? And getting it fast is not the only criterion. Another criterion could be how much money you pay to EGI or to Amazon or to wherever. Or how accurate the result is, because if you change the number of iterations that your system will run, the accuracy will change. And the environment is very different. How do you optimize in such environment? Open research area that needs to be solved in order for us to get the best designs. And here is just one little dinky 20 operator example with very weird stuff, going out, grabbing stuff from the web, running the model, imprecise data, and so on. This happens to be from some processing of user behavior in a portal of the national libraries across Europe. It doesn't matter, humanities, natural sciences, whatever. This kind of workflows are everywhere in these science. And they can be up to hundreds and thousands of operators that you need to run. So how do you build a system? And I won't go through all the details on the requirements to build a system that can handle any kind of operator in a distributed environment, be able to estimate on the parameters that optimization depends on, speed, accuracy, and so on and so forth, and come up with the best solution. We don't have a solution yet. People are working on it, we are working on it, but it's an open problem. And here's a picture of it. Let's say a few things about data analysis. Much statistical analysis is about finding patterns and trends. Various kinds. Traditionally, all the data are in files. And yes, you guessed right. I will say that if this is done inside the data management system, you'll take advantage of all the things that I talked about earlier if they are done right and appropriate for the kinds of data that your scientific problem has, and be a winner. Gain a lot in speed, accuracy, simplicity, and stuff like that. So if you look at, but the kind of, in addition to not dealing with files, also the data mining that the database people have been doing for the past 20 years has to change, and has to move away from a single track, clean the data, process it, run the mining algorithm, and so on, which pictorially is you get some data. I'm not asking you to read, third row what it has. You get the raw data, you curate it, you validate it, you clean it, and then you get a model around it. And then after you have the model, let's say Bayesian network or something like this, if you have a nice tool, you can play with it. And this is a system that we have been working on. But this is one side. This is not enough for the kind of challenges that we face with scientific data in this science. Before I give some of a particular example that shows the complexity that you may need to analyze, let me say that scientific data is about the ones that we observe, but let's not forget that scientists are generating the data that some other scientists, let's say social scientists, are interested in. So your behavior is data for some other scientist. And not only for some other scientists, but also for the people who have the systems and who care to know how you are using the system in order to improve it. So profiling users, scientists in this case, but in general, requires data analysis, your usage, the queries that you send, your clicks, and so on and so forth, much like you do it on the web, but all here in the scientific environment. And from there, you can get very useful information. Different kind of analysis, very important for what we're talking about. So, in order to handle what we need, you need a holistic, a so-called holistic approach. We have to move from a one-side track, clean model, interact paradigm, another paradigm shift. Okay, we want to look at it from many ways. And the traditional machine learning techniques use with one kind of data that are independently distributed and independently and identically distributed, okay, i.i.d. And they cannot handle uncertainty. But these need to be, we need to throw them away when we talk about scientific data analysis. We don't have complete knowledge. We have lots of noise and outliers. Again, from yesterday afternoon's talk, the interest is in the 7 outliers out of the thousands. That's maybe the next Nobel Prize, in the 7 outliers. There's no independence. So techniques like statistical relational learning, which are emerging, are the key, and we need to work with them in the context of scientific data. Let me give you a very simple example. I won't go into a particular scientific field. This is a very simple, if you want, ontology or schema for authors writing papers on topics funded by projects and so on. So things that, and of course, there is information that you care about that you cannot get elsewhere. You can only get it from analyzing indirect pieces of information, like usage, like going into text and summarizing it. So, question, you read a paper, what is the topic of the paper? Other than what is written next to the word topic on top, of course. Okay, you need particular data analysis for this. You have 2 papers by 2 people named Yannis Ioannidis. Is this the same Yannis Ioannidis? This is a common name in Greece. Okay, is it me? Okay, or someone else? Is this paper funded by someone? If it doesn't say partially supported by FP7 project, so and so, is it funded? Can you get this? The funders care about this as well. Can you detect people that belong to the same community and therefore they have the same language, and so that you can prepare appropriately by just looking at their behavior? Here is where the people come in. We're talking about scientific data, here publications, but it could be anything else. But users and usage of this data requires analysis in order for this science to be done better. And then, can you get the impact of a paper? Besides webometrics and bibliometrics, which are the simple things. Okay, more of that. Let me not spend it. And there is a lot of domain knowledge that you need to know, that you know that this Yannis Ioannidis is not the other, or that this mentioning without giving a reference number 13 there, in fact, is referencing that particular work, which is represented by the following 5 papers. It's multi-relational and so on. This kind of holistic approach is what we need in order to address the analysis of the data that we are facing in a scientific environment. And the technology is not there yet. We need to, data management people need to work on it, understanding the needs of the scientists. And here is a citation to us. Dissemination of results. Open access. There is quite a lot of discussion about open access. Okay, we're done our science, now we have to give it back to the world. What is open access? This is open access is not just access, is not just free access. Okay, it is accessing and using and reusing whatever you see in a free, for free by the user who is doing that. But it's not cost-free, it costs. But it's not the user who will pay. So there are lots of issues that need to be solved. But there's a lot of discussion about moving in that direction. And of course, the politicians love it. And we love it. The publishers don't love it. Any publisher among us? Okay. But they are trying to change their model as well. There are so many goods about open access, but the first thing that you are thinking about open access is, oh, my publications, my paper. I don't have to be an ACM member or an IEEE member to get it. Oh, IEEE is a publisher, okay? So the proceedings of this. But more and more in the fourth paradigm, we don't just publish papers. We also publish the data itself. The result of a scientific endeavor may not always be represented in the future as a paper. It may be represented as a URL where you go and there is a data set. And that's the contribution. Okay, you can complement it with a paper, but the data may be what will give you tenure. Of course, as faculty need to change our thinking about it, but this is where we're going. And so, when we talk about open science, we mean not about open access, use, and reuse of papers, but also of data, and of software, and of services that are generated in an appropriate way. And there are so many good things that come out of open science. Let me not go over them in the interest of time, but whatever a politician, whatever you think a politician would say about openness, okay, I would repeat. So there are a couple of projects, Open Air and Open Air Plus, that Europe has put together in order for all the publications that come out of its funding to be placed in publicly and openly accessible repositories. They're not up to data yet, but at least in terms of publications, open access to them is the objective, is the goal. And what's the purpose? Okay, open access publication repositories exist. There are about 1,500 around the world now, and growing. Of course, there are many more to be done. If every university is supposed to have one of these, and of course, there are many more than 1,500. And of course, there are thematic repositories, not by institution. You have information about the funding from the funding agencies, from various countries or federal states and Europe. And you may also have the data repositories. Okay, it's coming, as I said, it's not there yet, but you can imagine it. And these projects are trying to connect all this information, so funding information, publications, and data with the people who generated the publication or the data, who funded this research, or who is using the result. And of course, there may be some author who wrote a paper and his or her institution doesn't have a repository. What are they going to do? They are called orphans. The correct term is homeless. Okay, I don't have a home to put this. So there is a repository for the homeless, papers. Okay. So, and based on that, then you can capture and monitor and assess the impact of funding, of particular projects, of particular papers, of particular people, of particular areas, and so on and so forth. And many people love that. So that's the project. And the usage data is very important. And analyzing, you can imagine that analyzing the data that you get from satellites is hard, and it is. But analyzing the data from people is the worst. Because a pulsar, okay, at least for some period of time, is consistent. It's doing consistent things, okay? Humans, we are the most inconsistent thing in the universe, okay? Understanding that is very hard. So, from the usage to understand the impact is hard. Okay, let me talk a few things about interoperability. What is interoperability? Even on that, people cannot interoperate well enough to come up with one definition of what interoperability is. Okay, there are many, but let's stick to the first one, which is the IEEE, and I thought that I would use that because this is an IEEE conference. The ability of two or more systems or components to exchange information. And many people would stay there, okay, exchange data. But no, and to use that information that has been exchanged. Because just sending you information that is useless to you doesn't mean interoperation, okay? Even if you have correct mappings. So this applies predominantly to data, and there are many areas. This is a problem that has been around for 30, 40 years and will be around for another 1,000. Okay, there will always be interoperability issues. But because of multidisciplinarity in the sciences, it becomes, it reaches its worst situation. Semantic heterogeneity and scientific heterogeneity is the worst. How we can solve this? Lots of work needs to be done. Let me forgo the technical challenges. I want to emphasize that it's not just about the data. How you capture the users is very different. Different systems have different profiles of users. How do you capture policies? Big challenge. How do you capture in your systems policies? And if you want to interoperate, have compatibility of policies dealt with. You can standardize, but this is it's a very clean, but a very slow process, or you can mediate, which is quick and dirty. And we can never have the ultimate standard. There will always be something else that will come up and will need mediation. In data infrastructures, the question, shall we have one system that does it? Well, we have it for the networks. By now, I mean, the network is one thing. Well, we have it more or less for processing. EGI, Amazon, it's the same thing. And then some people say, okay, let's have it for data. Let's have one infrastructure for data. And I say that the buck stops here. We cannot, I don't believe that we can have one infrastructure for the data. Data infrastructures will be springing around everywhere with their idiosyncrasies of the communities that put them up. And then you'll have mediation, and then you have interoperability issues that you'll deal with. You can be abstracting and generifying some things and putting them into generic systems. But the concept of let's have the EGI for data or the giant of data is ill-defined. Okay? It's a different approach that needs to be done. The same is for software on top of data, functionality, users, communities, society. You cannot have one society or one community. Visions have been done. So let me conclude. We are living in the fourth paradigm in scientific research, and this will be with us for for a long time. The data size, but not only that, the complexity is fundamental for this science. There are many data management and analysis research challenges. It's not that the technology is there and some engineers will just put it together. Research problems need to be solved in order for the scientists to do their science well. And it's not their job to try to solve this problem. Interoperability is a huge challenge at various levels. And yes, there can be global research data infrastructures everywhere, capturing the globe, but not one, many. And the variety of them will need to interact and capture specific needs, interoperate at whatever level is necessary. All of this is in the name of science. But let's not forget, this science. Thank you.
Okay, thank you very much for this very interesting talk. I'm sure there's some questions. Yes.
Yeah, I guess I'll try to make it voice. First I have a comment actually on the layers of the infrastructure. You said that processing is more or less one thing. So I've been working for about, well, roughly 7 years or so on trying to run simulations on 2 disjoint pieces of compute hardware. To this day, I can definitely say it's not one thing. It's one of the biggest technical, scientific, but especially political challenges in the field to try and combine resources for one purpose.
I absolutely agree, yes. The complexity of dealing with the same things at the data level is much larger. So in that regard, computation is a much simpler problem. But I absolutely agree, especially, different types of clouds, let's say. The political thing, I won't even mention. You're absolutely right. But even technically, even at the technical level, yes, there are many issues. It's just that the data is, because semantics enter the picture, okay, it's one level higher.
Okay, so, and then the question I have is, earlier in the presentation, you mentioned about the data management and the data processing, and that it's, in, say, the third paradigm, it's done by scientists, and that should be outsourced to other specialists who are more suited for that part. So the thing I wonder about is, scientists are responsible for their papers. If I write a scientific paper about the basis of data, and there's a big mistake in that, then I'm responsible, and whoever is working underneath that, working with the data, is perhaps responsible for that local part, but I would be responsible for the paper as a whole. So when you outsource the data management and the data analysis, how do you ensure that responsibility is taken, and how do you validate as a scientist that these specialists do their work?
It's very hard to have a blanket answer to this. By trial and error, you gain the trust. One of the reasons why earlier the data management community has not been very interactive with scientists is that some early attempts were complete failures. And so there is big skepticism on the part of scientists on whether the data management community will be able to deliver. So you build the trust. In the same way, you don't ask, well, is Microsoft, the word processing that I do in my paper I'm writing, is what I see actually what I will get? Because, you've tried it a few times, not when you were writing your Nobel Prize paper, but something simpler. It worked, and then you build the trust. Software verification is an unsolved problem. So we cannot, in general, so we cannot have it for the data management. But you can have, next to the processing tools, you can have the testing tools. You can have validation tools to be examining things. And what is the criteria for validation is a question in itself, because the ozone data existed, and for some decades, the ozone hole data. And people were saying, oh, they're so off limits that probably there was some calibration error in the instrument, they're wrong. So even scientifically, how you validate the data is a big question. Certainly with synergy. I mean, and then building trust, and that's that. And still errors will happen, like they happen with anything else. But it's more a sociological issue, and then technical, of course, to build the right tools. Yeah, before you dance, you have to chat a little bit, you know, flirt a little bit.
You have to go out and have a beer with them together.
Yeah, yes.
Yes.
Absolutely, absolutely, yes.
Okay, thanks.
Okay, another question?
Thanks. Very good talk and interesting topic. And I just have a comment from the bio side that the data amounts on the bio side is increasing incredibly right now. We already have hundreds of terabytes, and that will probably be up in the petabyte range within a few years, because the machines generating the data will increase by a factor of 1,000 to 1 million within the next 8 years or so. So we all be in the same boat with the data deluge.
Good.
Okay, any other questions?
Yeah, there was over there.
It was actually the same.
Ah.
Elaborate on your notion that. So it goes in the same, it's actually the same question as my colleague. So EBI, the European Bioinformatics Institute alone, is building infrastructure for dealing with 10 petabytes per year, and it's only one institute. So I'm interested why you say or mention that the data volume in the bioinformatics area is kind of neglectable.
I didn't say neglectable. What I said, and maybe I didn't express it right, is that yes, the bio data is increasing, and the medical data is increasing dramatically as well. My impression, and I could be wrong, is that it's not increasing as fast as some of the natural sciences. I could be wrong there. But the most important comment I want to make is that bio, in addition to whatever size it has, the conceptual complexity around it is much larger than the natural sciences. So in the bio area, you have to deal with the conceptual complexity in addition to anything else. And that's why whatever we build for the astronomers is bound to not work for the biologists. We need to specialize, we need to try hard. Maybe some things will work, but there is this additional thing. And it's not just bio, okay? The humanities are extremely complex as well conceptually. So.
Do you have any examples of SciDB actually being used by scientists to do real science?
To the best of my knowledge, no, because it's still under development. But what they have been doing so far, I think it looks very nice. But it's not ready yet to be used.
Yeah, we use SciDB for doing big matrix calculations, and it works quite fine for us. But you're right, it's still under development, and it's not a final release product.
So I want to continue your discussion on open access. And you touched briefly, or you mentioned it in passing, that we also need open access to the data, the underlying data, and the various policies that people have to make the raw data that underlies their results publicly available. And if we are lucky, we have structural community repositories like in EBI, like at CERN, where data is kept. Whether we will understand this data in 10 years is a different question. I don't believe anybody in CERN still understands the lab data that they keep in their data vaults. But most of the cases, we just have a link to a homepage of a postdoc where the data is, and when a postdoc moves on, the data is erased. Nobody can understand this data. So I think we have a tremendous problem there. How are we going to solve that?
Preservation. This has nothing to do with open access, by the way. Yes. With respect to open access, let me make a parenthesis. The biological sciences have been pioneering this because there are many journals that don't allow you to publish your paper until the string of DNA or whatever data you discovered is deposited in a public repository, and then only your paper is published. So the rest of the sciences should move in this direction, I believe. Now, coming to your question, preservation. It's a huge problem, and it's one of these things that you think that it's either trivial or unsolvable. Probably it's the latter. Of course, you can put it under the carpet and make it trivial, okay? We keep everything, and we keep all the software, and we keep all the compiled software, and so on and so forth. But preservation is a big challenge. Humanity has survived by destroying things. Okay, you don't keep all your checkbooks, you know, and your parents' checkbooks and their parents' checkbooks and so on. There are some underlying criteria that people use to destroy things, get rid of things. We don't know how to do that with data or even publications, papers. There are many useless papers, you know, I've written some, so maybe we can get rid of them, okay? What is the criteria is unknown, and the ozone hole example is a case in point. People who thought they were wrong data, and thank God they didn't get rid of them, it proved very useful. So, big challenge. And of course, the big challenge is what you mentioned. Okay, we keep the useful data and only the useful data. How do you interpret the data? Okay, a paper, as long as there's one that can read, you know, the language, can interpret it and get it to the rest of the world. Data, I mean, EpoDB tapes that NASA has or had, I'm not sure if they still have them, lots of EpoDB tapes that no one has any idea of what they contain. So yes, that's big challenge, and some big money was put in it. I don't think very much came out of it because the problem is so complex. Not much, I mean, not much that can be in production use, but.
Okay, there's a couple of more questions. Yes.
Yeah. I'm working in a very heterogeneous environment. I'm working for a cluster of excellence called SimTech in Germany. There are around about 100 researchers focusing on simulation. There are biologists, chemists, sports scientists, philosophers, and so on. And we deal with multi-scale simulation workflows, with multi-domain simulation workflows, with multi-tool simulation, and so on, you name it. Therefore, no, we must focus on data on the biologist and data on the physics. We must combine both data. We must bring those things together to run a multi-star simulation.
What to do? Your question is?
It's more a comment. I think we don't have to think in one way. Okay, I must think in a biological way. I must think in a chemistry way. No, we are here in this conference. We have here lots about multi-scale simulation and so on. I think that's a wrong way to thinking in a biological data structure, in chemistry data structure. We must think, we must combine it. We must think in a federated biology and chemistry data structure.
Absolutely. I mean, multidisciplinary science, as I said, this science is predominantly now multiple phenomena, multiple disciplines, and so on. The question is, and it's a true question I don't have an answer to, in this case, is the right attempt, is the right approach to try to put everything around your arms under one umbrella, or will you get better results in having specialized formulations and then figure out where they connect? And there is a balance between the two, and it's maybe there are some rules, but we don't know them. We have to try and see where things are. But absolutely, that's...
Okay.
Right, so I think my question was already asked about data preservation, and I wanted to ask what are the criteria that one should consider to identify whether a piece of data should be preserved or not. So we answered that question. And I want to follow on that, whether it would be sensible in some certain cases instead, or one way of preserving the data would be to preserve the computation that either use the or produce the data? And a second question with respect to bio data, why it is complex. And I was wondering, from your point of view, is it complex because the computer scientists are not helping, because bioinformaticians or life scientists do not model the data well, they don't follow these any modeling principles, or because the data is complex, or because of all these things?
Okay. The first question, the criteria can be very many and broad on what you preserve and what not. It could be very frequently used, so you need it, okay? Very hard to regenerate, okay? The data that, I don't know, Voyager sends, you cannot easily, you know, wait another 20 years to send another Voyager, so you keep. Very rare data, so a phenomenon that is being repeated and repeated, you can just abstract and statistically approximate. But something that is very different, maybe peculiar, you keep it because you saw it. A whole bunch of other criteria. Now, which combination depends on the case, and there is no fixed set of criteria. But here, these are some of the things that people have proposed and used. With respect to the second one, the biological sciences are the ones where informaticians have collaborated the longest and the most intensely. For whatever reason, bioinformatics, I think it was probably the first or one of the very first science-informatics field that was generated. Maybe because DNA is like a program. I don't know, I'm not sure why it's biologically, biology is exciting to informaticians. I'm not sure. The complexity, so it's not because people have not worked enough. It's certainly not because the biologists don't model the data well. Every scientist understands their data in the best way. And with modeling expertise from data modelers, okay, not every data management person is a good data modeler, okay, what you get is best. I think that the complexity of the data itself is the main reason, okay?
Okay, I think we have to, there are several more questions, but I think we have to stop to be able to have some coffee. But before that, I would like to thank you again, and thank you for having such a nice keynote lecture.
Thank you very much. It's a pleasure.
And the discussion can continue at the coffee break.
Absolutely.
Thanks.